Next we move on to Kripke structures. So these are similar to label transition systems, except now you notice that we have no actions taking us from one state to another state. And you'll also notice that instead of our states simply being called 0, 1, 2, 3, and 4, that we now have atomic propositions as part of our states. So let's just go through what a Kripke structure is and the differences to a label transition system. So we're calling our Kripke structure K in this instance. So KS is short for Kripke structure, and this KS we're calling it K. So a Kripke structure consists of a 5-tuple. So S, which is a set of states, I, which is an initial state, same as the LTS. So now we have atomic propositions. As we stated earlier, these have to be true or false. Assertions that are either true or else they are false. We have transitions, and we also have labels. So S is a set of states. So once more, we have our 1, 2, 3, 4, 5 states. We call them 0, 1, 2, 3, 4, 5 once more. And our cyber Kripke structure is again the cardinality of S, so it's the number of states we have. I, again, is a set of initial states. Once more, it's a subset of S, so again, it is denoted by this arrow coming in here to our state 0. Now we have atomic propositions, so it's a set of atomic propositions. AP is a statement or assertion that must be true or false. So in our Kripke structure K, we've just written in the atomic propositions into the state name just so you can see what they are. So at state 0, we see that white is true. In state 2, black is true. In state 1 again, white is true. 3 black, 4 black. So we say our set of atomic propositions is white and black. These are our two atomic propositions for Kripke structure K. So when we do traversals of this Kripke structure with our temporal logic, we will be determining whether white is true at state 0. Is black true at state 3? And because these are atomic propositions, they have to be true or false. So this black will be true at 3, but white will be false at 3. Again, we have a transition, is a total transition relation. But you notice that now we don't have actions. It's just S, X over to S prime. So it's just straight transition. So if we're in state 0, we can freely transition to state 2. In state 2, we can transition to state 1. We can transition to state 3. It's either or. So it's not related to an action as it was in the label transition system. So just notice that we don't have any, remember in the label transition system in our previous video, we had A and we had B here to determine where we're going to go based on our action. Now we don't have these. Now we just transition freely. And finally, L is a state labeling. So L, S goes to 2 power of AP. So this is known as the power set. So because our atomic propositions must be true or false, so essentially they are booleans, the number of labels we can apply to a state is 2, because it is binary, boolean, to the power of the number of atomic propositions we have. So let's explain. So we have atomic propositions white and black. So we have 2 atomic propositions. So 2 to the power of 2, if we have in here, will give us 4. So in state 0, so in every single state, we can have 4 different labels, 4 different types of labeling. What are these? So every power set we can have, let's see if I can get a pen. I will go to the whiteboard. Two to the power of AP. So our set of atomic propositions are white and black. That is our atomic propositions. So the labels for our sets. So what labels can we apply to each state within a Kripke structure? So again, we have 2 to the power of, we have 2 atomic propositions. So our power set, we have 4 possibilities in our power set. So our power set basically is just all the combinations we can possibly have. So think of a power set as all the set of sets we can possibly have. So, boom. So we have a set of sets. And we can have 4 different sets. For our Kripke structure K, from our example here. These are, well, in every power set, you always have possibility of neither. So the empty set. That will always be one of your power set. You will always have the ability to have the empty set. You will also have the ability to have all the atomic propositions true. So you can have white and black. And you also have the ability for one true, so white, or the other, black. So this is what we're seeing. In each state, label for our states, we have this power set, which is denoted here by 2 to the power of AP. That's what our power set is denoted by. And in this, the number of sets we can have are the empty set, we can have white, we can have black, or we can have white and black. So if we go back here we have white, that's valid, we saw that. We have black, we have white, we have black, and we have black. So here we've used 2 of the available sets of our power set. We have not used, we have used white and we have used black. We have not used white and black, and we have not used the empty set. That is what this section is about. So again, we have a set of states, same as level transition system. We have an initial state, same as the LTS. We have atomic propositions that now must be true or false at every state. We have a transition relation which does not rely on actions anymore. We can just transition. And we have labels in a state, and your available labels is our power set, which is denoted by 2 to the power of AP. Because it is Boolean, it's the number of atomic propositions, 2 to the power of the number of atomic propositions we have. So part 2, let's go into paths. So path is denoted here by that. That's the pi. It's denoted here by pi. Starting in state as is a sequence of states. So pi here, or path, let's say path instead of that, is S, S1, S2, S3, S4, such that one state transitions to next state. So S transitions to state 1. S I minus 1 transitions to S of I for all I greater or equal to 1. So this was basically saying S I minus 1, so S of 1 let's say, goes to S of I 2. So 2, let's say this is I, 2 minus 1 is our previous successor. So that is our predecessor. This is the successor. Basically, every state that you can reach has a predecessor. Basically, that's all that's saying. And if you're in a current state, you can transition to a successor. That's all that's basically saying. So our question. So we have a path 0, 2, 3, 2, 1, 1, 1, etc., etc. The path at index I is the state at position I. And notice that I always begins at 0. So if we have our path, or pi, I dot 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 notation, that means it's the suffix of the path starting at position I. And if we have our path, or dot 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 I, that means it's the prefix of the path starting at position I. So this is just some notation. So I have to say what are the states for the path above. So this path, at path of 0, now I always begins at 0, so this is just the first path value, so it's going to be 0. Pi index 3, so what is our value? It's going to be 0, 1, 2, 3, so it's going to be state 2 is the answer to this question. Maybe I'll do this. So first section, pi 0 is on our pad 0, 2. I will expand this up. So we have a pad 0, 2, 3, 2, 1, 1, 1, dot, 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 dot. That goes on forever. That just means it's infinite when you have a dot, dot, dot at the end. It's going to be stuck in 1 forever. So n of 0 is going to be at our first index, so it's going to be 0. Pi of 3, index 3, so this is index 0. This is index 1, index 2, index 3, 4, 5, 6. It's the same as you would as in Java. So 3 is 0, 1, 2, 3, so it's our value 2. Is for question 2. Now for question 3. Two dot dot dot. So this means it's a suffix of the path starting at position I. So I is 2, 0, 1, 2. So 3. And we want the suffix. So it's 3, 2, 1, 1, 1, dot 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 forever. So that is what this is. So suffix basically means everything at the end. So after index 2. Prefix means everything before the index. As in the next question, we have dot 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 5, so it's the prefix from index 5. So 0, 1, 2, 3, 4, 5 is 1. What is the prefix of it? So we have 1. We have a 2. We have a 3. We have a 2. We have a 0. So it's everything before prefix 5. Now you can equally go 0, 2, 3, 2, 1, 1. In fact, I would probably recommend to use this style. Start at 0 and work your way all the way up until you get to index 5. So, I just showed you here how you can do what it means. You start at 5 and go back, but you can just as easily go the other way. So start at index 0 and work all the way up and stop at index 5. So 0, 2, 3, 2, 1, 1, 1. And finally, you can see this one, which is pi 0 dot dot dot. So this is the suffix starting at index 0. Well, that is just pi. That is your path. That is just your path. Starting at 0 and everything coming afterwards is the exact same as this. You start at 0, you get 0, you get 2, you get 3, you get 2, you get 1, you get 1, 1, and it goes on infinitely. So it's the exact same thing. And that is it for part 2.